All right, let's do one more free fall problem. This one I'm going to go the other way with it. Let me get my markers. Let's say in this case that we have, I don't know, a boot. Let's throw a boot up in the air. Wow, that's a good marker. Let's throw a boot up in the air. Yes, I did make that shot. And let's say we threw it at a speed down here of 12 meters per second. Right? Seem reasonable? 12 meters per second. And I want to know what's the height? How high did it rise? How high did it go? You may seem like, well, geez, that's not very much information. Well, let's see what we get. Motion problem. First question is there acceleration? Yes, there is. This is a free fall problem. Okay, this is a free fall because while this boot is in the air, it's only subjected to gravity, just like my tennis ball here. When I throw it up, it's only subjected to gravity. That's what pulls it back down. It's still a free fall problem. Free fall problems have acceleration because of gravity. And if it's accelerated, that's a kinematics problem. So here we go. A, T, V, B, and D. A, T, V, B, D. Acceleration, time, initial velocity, final velocity, displacement. Do we know acceleration in the problem? Yes, we do. It's gravity. And gravity is always negative 9.8 meters per second squared. Do we know the time? No, we do not. Doesn't tell us. Do we know the initial velocity? That's the first velocity this boot experiences. Yes, we do. That's the 12 meters per second. Do we know the final velocity? You may be thinking, well, no, we don't have the final velocity, but let's think about it. When my ball is flying up in the air right here, at the top it does what and then comes back down? It stops. It stops, and for a moment the speed is 0 at the top. So at the top of any free fall problem, before this ball begins to come back down, the speed up here is 0. And so if we're just talking about the trip up, speed is 0, that's the final velocity. The distance, I don't know. In fact, that's what we want to find. So I'll come over here to my U. I don't know T. I don't know delta D. Delta D is what I want to know. That's my height. That's the distance that this thing travels upward. If I want to know this, I don't care about this. So I have to find an equation that has delta D and not time. So here we go. I'm going to look at my equation chart, and I am finding this equation. Vf squared equals Vi squared plus 2a delta D. That's our equation. It's got delta D in it. It does not have time in it. So let's plug in and solve. Vf is 0. Vi is 12 plus 2. A is negative 9.8. And D is what we don't know. Now, let's stop right here, and I want to consider direction again. V we said was positive, and that's true because in this case, the velocity starts out going upward. Up is positive, so we need to give this a positive value. Delta D we should think about as well. That's what we're looking for, but if we're going upward, this is going to be a positive displacement. So we should end up with a positive delta D if we did everything right. So here we go. Let's work this out. 12 squared is 144, so 0 equals 144 plus 2 times negative 9.8 is a negative 19.6. And you end up with delta D. Start out isolating delta D by subtracting 144 from both sides. So negative 144 equals negative 19.6 delta D. Divide now by negative 19.6. That goes away. Delta D is what's left. And we do 144 divided by 19.6. I can do that because my negatives go away. They become positive. And I end up with a delta D, a height of 7.3 meters. rises to a height of 7.3 meters.